Welcome to this coding walkthrough. Today, we will tackle the classic dynamic programming problem, house robber, which is a popular problem in coding interviews. We'll explore different approaches to solve this problem efficiently, including brute force and optimized solutions. Let's dive in. In this problem, you are a professional robber planning to rob houses along a street. Each house has a certain amount of money hidden inside, and your goal is to maximize the total amount of money you can steal. However, there's a key rule that makes things tricky. If you rob two adjacent houses on the same night, their security systems will trigger an alarm, and you'll get caught. To solve this, you need to carefully plan which houses to rob to maximize your haul without setting off the alarm. The input to this problem is an integer array called nums, where each element represents the amount of money stored in a specific house. Your task is to return the maximum amount of money you can rob without robbing two directly adjacent houses. Let's look at some examples to clarify. In the first example, the input is nums equals 1, 2, 3, 1. Here, the optimal strategy is to rob the first house, which has 1 unit of money, and the third house, which has 3 units of money. By skipping the second house, you avoid triggering the alarm, and your total earnings are 1 plus 3, which equals 4. So, the output for this example is 4. In the second example, the input is nums equals 2, 7, 9, 3, 1. The best choice here is to rob the first house with 2 units, the third house with 9 units, and the fifth house with 1 unit. Adding these together, you get a total of 12, which is the maximum amount possible without alerting the police. Now, let's consider a simpler example. If the input is nums equals 0, there's only one house, and it has no money. Since there's nothing to rob, the maximum amount you can steal is 0. This example highlights the importance of considering edge cases in the problem. Speaking of constraints, the length of the array nums can range from 1 to 10,000, and the amount of money in each house, represented by nums, I, can be between 0 and 10,000. This means your solution needs to handle both small and very large inputs efficiently. It's also important to think about additional edge cases. If the array contains only one house, the solution is straightforward. You simply return the value of nums, 0. If there are 2 houses, you return the maximum of the 2 values, as you're allowed to rob just one of them. Another scenario to consider is when all houses have 0 money. In this case, the output should simply be 0, since there's nothing to rob. Lastly, the problem requires handling large arrays up to the constraint limit of 10,000 houses, with varying amounts of money stored in each. Your solution must be optimized to handle these larger inputs efficiently without running into performance issues. To solve the house robber problem, we start by considering the brute force approach. The intuition here is straightforward. We explore all possible combinations of houses to rob while ensuring that no 2 adjacent houses are chosen. This can be modeled using recursion, where at each house, you decide to either rob it and skip the next house, or skip it and move to the next one. This generates a recursive tree structure, where each node represents a house, and the branches represent the choices to rob or skip. However, there are some key observations about this approach. First, the problem can be broken into smaller subproblems, and the solution to the overall problem depends on the solutions to these subproblems. Unfortunately, this method has a time complexity of O2 to the power of n, since every house creates 2 choices, leading to exponential growth. It also has a space complexity of O(n) due to the recursion stack. While this approach is simple to implement, it becomes highly inefficient for large inputs because of its exponential nature. To improve on this, we can turn to dynamic programming with memoization to eliminate redundant calculations. By using the dynamic programming top-down approach, we introduce memoization to store solutions to overlapping subproblems in a cache. This means that for each house, if the solution has already been computed, we can directly retrieve it from the cache instead of recalculating it. If not, we compute it recursively and store the result for future use. This approach is more efficient, as it reduces the time complexity to O(n), since each house is processed only once. However, it still requires O(n) space due to both the recursion stack and the memoization table. To optimize further, we can switch to the bottom-up dynamic programming approach. Here, instead of recursion, we solve the problem iteratively, building solutions for smaller subproblems step by step. The key insight is that at any house, the maximum money robbed so far is the greater of two options, either the amount robbed up to the previous house, or the amount robbed 2 houses before plus the money at the current house. This allows us to replace the memoization table with just 2 variables, significantly reducing space usage. With this, the time complexity remains O(n), but the space complexity improves to O(1), making this approach both time and space efficient. For this problem, we chose the dynamic programming bottom-up approach because it offers the best balance between efficiency and simplicity. Unlike the brute force and top-down methods, this approach avoids the overhead of recursion and minimizes memory usage, making it well-suited for handling large inputs. The key breakthrough was recognizing that to compute the maximum money robbed at any house, we only need the results from the last 2 computations. This eliminates the need for a full memoization table and allows us to achieve O(1) space complexity while keeping the logic straightforward and readable. By leveraging the problem's subproblem structure and constraints, this strategy stands out as the optimal solution, suitable for both competitive programming and real-world applications where performance is critical. Here, the problem is to determine the maximum amount of money you can rob from a series of houses arranged linearly, with the restriction that you cannot rob 2 adjacent houses. Each house has a certain amount of money, represented as an array nums, where each element corresponds to the money available in that house. To solve this, we start by clearly defining the problem. We need to maximize the total money robbed while adhering to the constraint of skipping adjacent houses. At each house I, we make a decision between 2 choices. The first choice is to rob the house, which means adding the money in nums, I, to our total and skipping the next house by moving to I plus 2. The second choice is to skip the house, moving directly to the next house I plus 1 without adding anything to the total. Mathematically, this decision can be expressed as dp I equals max nums I plus dp I plus 2 dp I plus 1. This equation forms the foundation of our algorithm, as it captures the essence of the problem, whether to include or exclude the current house to maximize the total amount robbed. In this equation, dp I represents the maximum money that can be robbed starting from house I. To make this recursive approach work, we need to define the base cases. If I is out of bounds, meaning I equals n, then there are no houses left to rob, and the result is 0. These base cases ensure that the recursion terminates. However, recursion alone can become inefficient due to repeated calculations for overlapping subproblems. To address this, we employ memoization, storing the results of dp I in a cache so that they can be reused without recalculating. This cache can be implemented as an array memo of size n, initialized to -1 to indicate uncomputed values. To further optimize, we transition from recursion to an iterative dynamic programming approach. Instead of solving the problem top-down, we compute results bottom-up. Starting from the last house and moving backward, we maintain a dp array where each element dp I holds the maximum money that can be robbed starting from house I. The transition remains the same, dp I equals max nums I plus dp I plus 2 dp I plus 1. This iterative approach eliminates the overhead of recursive calls, making the algorithm more efficient. To optimize space complexity, we observe that the value of dp I depends only on the next 2 values, dp I plus 1 and dp I plus 2. This allows us to replace the dp array with just 2 rolling variables, previous 1 and previous 2, which represent dp I plus 1 and dp I plus 2, respectively. The transition relation becomes current equals max nums I plus previous 2, previous 1, after which we update the rolling variables as previous 2 equals previous 1 and previous 1 equals current. This reduces the space complexity from O(n) to O(1). To summarize the key insights of our approach, first, the recursive choice simplifies the problem to deciding whether to include or exclude the current house. Second, we define clear base cases to terminate recursion. Third, memoization ensures that overlapping subproblems are solved only once, improving efficiency. Fourth, transitioning to an iterative approach enhances control and avoids recursion stack overhead. Finally, space optimization using rolling variables achieves the same results with significantly reduced memory usage. We also use data structures like the dp array in the initial iterative implementation or rolling variables in the optimized version to manage intermediate results. These elements come together to form an efficient and scalable solution. The optimized dynamic programming approach is implemented in Python is shown here. We first handle edge cases. If the array nums is empty, we return 0 since there are no houses to rob. If there's only one house, we return the amount in that house. For two houses, the result is the maximum of the two amounts. After handling these cases, we initialize two variables, previous 2 and previous 1, to 0. These represent the maximum money robbed from the two subsequent houses. Starting from the last house and moving backward, we calculate the current maximum money as max, nums, I, plus previous 2, previous 1, update previous 2 to the value of previous 1, and set previous 1 to the current maximum. This rolling update ensures that we are always working with the most recent two values, maintaining the correctness of the calculation while using constant space. Finally, we return previous 1, which contains the maximum money that can be robbed starting from the first house. The algorithm handles edge cases like empty lists, single houses, and large inputs efficiently, ensuring its robustness. In terms of complexity, the time complexity of this solution is O(n), as we iterate through the list of houses exactly once. Each house is processed in constant time, making the algorithm efficient even for large inputs. The space complexity is O(1) in the optimized version, as we use only two rolling variables to store intermediate results. This reduction in space usage is achieved without compromising the correctness or efficiency of the algorithm. By optimizing both time and space, this approach provides a practical and scalable solution to the house robber problem, making it suitable for a wide range of input sizes and scenarios. This solution tackles the house robber problem, which seeks the maximum money that can be robbed from a row of houses while skipping adjacent houses. Here's how the code works. Initial checks. The first two conditions handle edge cases. If there are no houses, nums is empty, the function returns 0. If there's only one house, the maximum money is simply the value of that house. Dynamic programming variables, two variables, previous 1 and previous 2, are used to maintain the maximum money robbed up to the last house, previous 1, and the house before the last, previous 2. This eliminates the need for auxiliary space like a DP array, reducing space complexity to O(1). Iterative calculation. The loop iterates through each house's money number. For each house, the maximum amount that can be robbed is calculated as max, previous 1, previous 2 plus number. This decision ensures that either the current house is skipped, previous 1, or included, previous 2 plus number. Update variables. After calculating the best choice for the current house, previous 2 is updated to the old previous 1, and previous 1 is updated to the new maximum, current. This prepares the variables for the next iteration. Final result. After processing all houses, previous 1 contains the maximum money that can be robbed without violating the non-adjacency constraint. This approach is efficient with O(n) time complexity and O(1) space complexity, making it optimal for large inputs. By leveraging dynamic programming principles and minimizing space usage, this solution is both elegant and robust. This is the Java implementation of LeetCode problem number 198, house robber. The logic mirrors the Python solution, with type declarations and a class structure as per Java conventions. The use of variables previous 1 and previous 2 eliminates the need for additional space, maintaining an O(1) space complexity. The algorithm iterates through the input array nums, updating the maximum amount robbed dynamically. The final result is returned as the maximum money that can be robbed without alerting the police. To understand the solution, let's start with an example where we have houses with values 2, 7, 9, 3, 1. Our goal is to determine the maximum money we can rob without ever robbing two adjacent houses. We begin by initializing two variables, previous 1 and previous 2, both set to 0. These represent the maximum money robbed up to the previous house and the house before that, respectively. Now, processing the first house, which has a value of 2, we calculate current as the maximum of previous 1 and previous 2 plus number. Substituting the values, we get max, 0, 0 plus 2, which is 2. We then update previous 2 to previous 1 and previous 1 to current, so previous 2 becomes 0 and previous 1 becomes 2. Next, for the second house, with a value of 7, the formula gives us max, 2, 0 plus 7, which is 7. Updating again, previous 2 becomes 2 and previous 1 becomes 7. For the third house, with a value of 9, the calculation is max 7, 2 plus 9, resulting in 11. After the update, previous 2 becomes 7 and previous 1 becomes 11. Now, processing the fourth house, which has a value of 3, we calculate current as max, previous 1, previous 2 plus number. Substituting the values, we get max 11, 7 plus 3, which equals 11. After updating, previous 2 becomes 11, and previous 1 remains 11. Finally, we move to the fifth house, valued at 1. The formula gives us max 11, 11 plus 1, resulting in 12. Updating for the last time, previous 2 becomes 11 and previous 1 becomes 12. At the end of this process, the value of previous 1, which is 12, represents the maximum money we can rob from this row of houses without violating the condition. Let's look at another example with houses valued at 1, 2, 3, 1. As before, we initialize previous 1 and previous 2 to 0. Starting with the first house, which has a value of 1, the calculation for current is max, previous 1, previous 2 plus number, giving us max, 0, 0 plus 1, which equals 1. We update previous 2 to 0 and previous 1 to 1. For the second house, with a value of 2, the calculation becomes max, 1, 0 plus 2, resulting in 2. After updating, previous 2 is set to 1 and previous 1 to 2. Next, for the third house, valued at 3, the formula gives us max, 2, 1 plus 3, which equals 4. Updating once more, previous 2 becomes 2, and previous 1 becomes 4. Now processing the fourth house, which has a value of 1, we calculate current as max, previous 1, previous 2 plus number. Substituting the values, we get max, 4, 2 plus 1, which equals 4. After updating, previous 2 becomes 4, and previous 1 remains 4. The final output here is the value of previous 1, which is 4, representing the maximum money that can be robbed from this set of houses. Next, we'll consider a slightly larger example with houses valued at 5, 5, 10, 100, 10, 5. We start by initializing previous 1 and previous 2 to 0. For the first house, with a value of 5, the calculation for current is max, 0, 0 plus 5, which gives us 5. After updating, previous 2 is set to 0 and previous 1 to 5. For the second house, also valued at 5, the formula gives us max, 5, 0 plus 5, resulting in 5. Updating again, previous 2 becomes 5, and previous 1 remains 5. Moving to the third house, with a value of 10, the calculation becomes max, 5, 5 plus 10, which equals 15. After updating, previous 2 is set to 5, and previous 1 becomes 15. For the fourth house, valued at 100, the formula gives us max, 15, 5 plus 100, resulting in 105. After updating, previous 2 becomes 15, and previous 1 is now 105. For the fifth house, with a value of 10, we calculate max, 105, 15 plus 10, which equals 105. Updating, previous 2 becomes 105, and previous 1 remains 105. Finally, for the sixth house, valued at 5, the calculation is max, 105, 105 plus 5, giving us 110. After the last update, previous 2 becomes 105, and previous 1 becomes 110. The final output for this example is the value of previous 1, which is 110. This represents the maximum amount of money that can be robbed from this sequence of houses without ever robbing two adjacent houses. By following this step-by-step process, we're able to optimize our solution efficiently using constant space and iterating through the list just once. This approach ensures that we achieve the optimal result while minimizing computational overhead. The time complexity of the solution is O(n), where n represents the number of houses in the nums array. Let's break this down step by step. First, the initialization phase, which includes checks for an empty array or a single element array, takes constant time, O(1). Next, the main computation happens within the for loop. This loop iterates through each element in the nums array exactly once. During each iteration, we perform a simple comparison to calculate the maximum of two values, which is an O(1) operation, and then update two variables, previous 1 and previous 2, which are also constant time operations. So, the loop as a whole runs in O(n) time. Finally, the return statement at the end is a straightforward operation that takes O1 time. When we add all these components together, O1 for initialization, O(n) for the loop, and O1 for the return, the overall time complexity simplifies to O(n). The space complexity of this solution is O1, meaning it uses only a constant amount of extra memory regardless of the size of the input. This is achieved by efficiently using a few variables to store intermediate results during the computation. Specifically, the algorithm uses previous 1, previous 2, and current to keep track of the maximum amounts robbed up to certain points in the array. These three variables occupy a fixed amount of memory and do not grow with the size of the input array. Additionally, the input array nums is not modified, so no extra space is allocated for it. Since the algorithm avoids using additional data structures like arrays or hash maps, the auxiliary space usage remains constant at O1, making it extremely space efficient. A comparison with the naive approach helps highlight the efficiency of this optimized solution. In a brute force method, we would recursively explore all possible combinations of houses to rob, ensuring that no two adjacent houses are included. For each house, there are two choices: either rob it and skip the next, or skip it and consider the next house. This results in an exponential number of combinations, leading to a time complexity of O2 to the power of n. On the other hand, the optimized solution leverages dynamic programming principles. By maintaining two variables, previous 1 for the maximum money robbed up to the current house, and previous 2 for the house before the previous, it avoids recomputing overlapping subproblems. The algorithm iterates through the array just once, reducing the time complexity to O(n), and uses only constant space, O1, for intermediate calculations. This represents a significant improvement over the naive approach. When analyzing this algorithm, we find that its efficiency remains consistent across all scenarios. In the best case, the input array is empty, and the algorithm immediately returns 0 with a time complexity of O1. In the average case, the algorithm processes an array of size n, performing O1 operations for each element, resulting in a time complexity of O(n). Even in the worst case, where the array contains n elements and every element is processed, the time complexity remains O(n). To prove this, we note that the loop iterates n times, and each iteration involves constant time work. Multiplying the number of iterations, O(n), by the work per iteration, O1, confirms the total time complexity is O(n). The space complexity is similarly straightforward. The algorithm uses only three variables: previous 1, previous 2, and current, regardless of the input size. Since the memory usage does not grow with n, the space complexity is O1, making this solution highly efficient for both time and space. When solving the house robber problem, there are several common mistakes to be aware of. First, not handling base cases properly can lead to issues. For example, if the input list of houses is empty, or contains just one house, failing to account for these edge cases can result in runtime errors or incorrect results, such as trying to access invalid indices. Another mistake is making incorrect assumptions about the constraints. If you assume the number of houses is always large or the inputs are always valid, you might overlook simpler scenarios, leading to solutions that are unnecessarily complex or fail for small inputs. Additionally, using a brute force approach without addressing overlapping subproblems is a significant pitfall. This leads to exponential time complexity, as the same subproblems are recomputed multiple times, making the solution inefficient for larger inputs. Finally, ignoring space complexity can be problematic. If you're using recursion without memoization, the recursive depth may exceed system limits for large inputs, leading to stack overflow errors. Each of these mistakes highlights the importance of careful problem analysis and efficient implementation. Another common mistake in this problem is misunderstanding the non-adjacent constraint. If you include adjacent houses in your solution, you're breaking the core rule of the problem, which will inevitably result in incorrect results. Now, in terms of insights for interviews, this problem is essentially a variation of the classic maximum sum of non-adjacent elements problem, which is a staple in dynamic programming questions. The optimal approach involves using dynamic programming, and you can further optimize space by maintaining only two variables to track the last two states, achieving O(n) time and O(1) space complexity. A key insight is that for each house, you need to decide whether to include its value, which involves adding it to the maximum value 2 houses back, or exclude it, which means taking the maximum value up to the previous house. When explaining your solution in an interview, it's crucial to clearly articulate your thought process, especially how you derive the state transition relation in dynamic programming. This demonstrates both your understanding and your ability to communicate effectively. The house robber problem is closely related to several other problems. For example, LeetCode 53, maximum subarray, uses Cadon's algorithm and shares similarities in optimizing sums. Of course, the classic version of house robber itself is a foundational problem, but there are variations like LeetCode 213, house robber 2, which introduces a circular house arrangement, and LeetCode 740, delete and earn, which involves weighted sums. Exploring these related problems can deepen your understanding of dynamic programming patterns. Now, let's consider alternative approaches to solving the problem and the trade-offs involved. A brute force solution has a time complexity of O(2 to the power of n, due to the exponential number of combinations and uses O(n) space for the recursive stack. While it's simple to implement, it's impractical for large inputs. A more efficient approach is dynamic programming with memoization, which reduces the time complexity to O(n) and the space complexity to O(n) by storing intermediate results. However, it requires extra memory for the memoization table, which can be a trade-off in memory-constrained environments. The most efficient approach to solving this problem is dynamic programming with space optimization. By maintaining only the last two states, you can achieve O(n) time complexity and O(1) space complexity. This is highly efficient, but it requires careful attention to how the states are updated to avoid errors. Another effective option is the iterative approach, which also has O(n) time complexity and O(1) space complexity. While it's similar in efficiency to the space-optimized dynamic programming method, some beginners might find it less intuitive because of the way the transitions are handled. Both of these methods highlight the importance of balancing efficiency with clarity when designing your solution. Understanding these trade-offs can help you choose the best approach depending on the constraints and requirements of the problem at hand. Great work! We've wrapped up the house robber problem, highlighting its dynamic programming solution and a space-optimized approach. Remember, mastering problems like these builds a strong foundation for tackling more complex challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!